Okay, I want to take a minute to look at what we call the parent functions, some very basic uh, functions that provide the foundation for learning about transformations. Okay, and so these are six functions you're probably familiar with. We're just going to make sure that we get them all out there and that everybody understands some of the finer points, I suppose, of them. The first one we look at when we talk about the parent functions is just your basic linear function. Okay. Now, normally a linear function is written in slope-intercept form like so, right? You're familiar with this. Now we replace the y with f of x. Okay. And the absolute most basic linear function we can look at is a linear function that has a slope of 1 and a y-intercept of 0, right? Which is what we see here. This is also referred to as the identity line, which we will be discussing a little bit more when we talk about inverse functions. Okay, so a linear function in its most basic sense is a function with a slope of 1 and a y-intercept of 0. Okay? Constant functions are horizontal lines. Okay, so a constant function, now you should remember this from your time in algebra, but you should remember that anytime we have an equation where it's just y equals some number, that's a horizontal line at that number. Now, in terms of being a function, again, we replace y with f of x. And if we say f of x equals 4, there's nowhere in the function to put a value of x, right? So for example, like this point right here has coordinates -5, 4. This point right here has coordinates 0, 4. Over here, we're at 7, 4. There's nowhere in a constant function to put these x values. It's basically just saying it doesn't matter what the input is. The output's going to be 4. I can put anything I want here, but it's going to be 4 when it comes out, right? And so that's just a function approach to this idea of a horizontal line that you learned about since you were in algebra, right? So a quadratic function, something you're probably familiar with at this point. Again, a quadratic function shows up as a parabola when we graph it, a basic quadratic function like so. In a future lesson, we're going to be looking at quadratic functions that are in standard form, okay? Or sometimes referred to as vertex form, right? And when we get to that, not to ruin the ending too much, but the values that go here and here and here are going to transform this. They're going to make it skinnier. They're going to flip it over. They're going to move the whole thing. They're going to shift it, okay? But a basic parent quadratic function has its vertex at the origin, okay? So if you're unfamiliar with this term, the vertex is that point where the graph goes from decreasing, right? From decreasing to increasing or vice versa. Okay. And the vertex for a parent or a basic quadratic function is at 0, 0. And we're really going to focus on this vertex when we start to transform these functions. Okay. A cubic function doesn't get as much airtime as a quadratic function. Okay. Doesn't have a special name, at least not one that we're going to look at. It doesn't have a vertex. Okay. But what it does have is it has this point right here, which does have a special name, and we call this the inflection point. Now, the graph doesn't necessarily change its behavior at its inflection points. For example, this graph is always increasing if you look at it from left to right. Okay, so this cubic function is always increasing. But at the inflection point where we think we may see a change in behavior, we don't. Okay. I know it's kind of a non-math term, but this is where the wiggle happens. Okay, when we see a wiggle in the graph, that's our inflection point. And a basic cubic function has its inflection point at 0, 0. Okay, and any cubic function, I forgot to mention this about quadratics, but any cubic function can have extra terms, right? We can have extra x terms in here. We can put parentheses around something like this. Okay, and then add some stuff here and add some stuff here. We're still going to end up with x cubed as our highest exponent, or the degree of this function is 3. Like we like to call that highest exponential value. We like to call that the degree. So for a cubic function, the degree is 3. A basic as basic can get cubic function is just x cubed, and this is the behavior that we see out of that. Absolute value functions. Okay, absolute value functions are similar to quadratics in form, where we see it has symmetry with respect to the y-axis. We can call this a vertex. okay, we can call the vertex the origin here for a basic absolute value function. And why does it look like this? Because it doesn't matter if I put a -5 or a +5 in here, the output is going to be positive, right? And we're going to start messing with these with numbers outside here, inside here, numbers in front, okay? But a basic absolute value function looks like this V graph, okay? And it has this symmetry. It has a line of symmetry that cuts right through the middle of that vertex, all right? A root function, or sometimes referred to as a radical function, looks like this. And the best way to think of a root function, okay, and we're going to talk a lot more about this when we start talking about inverses, but it's really half of a sideways parabola, okay? My drawing's not going to be perfect, right? But when you think about what a parabola would look like on its side, it would look like this, okay? And so when we start talking about inverses, if we had a function, excuse me, f of x equals x squared, and we got a parabola, when you start talking about taking the inverse of this, what's the inverse of squaring something, right? The inverse of squaring a number is taking its square root. Okay, so that's just laying a bit of the foundation down. But we can't have a radical function do this, because if it did that, it wouldn't pass the vertical line test, right? Okay, so a root function is a sideways parabola, but we only include the top half of that. The one thing you want to be careful for when we start talking about, sorry, let me change this. Then we start talking about transforming a radical function is you always have to be aware of where that radical is. Okay, so just as a starting off point, when we're looking at radical functions, these sideways parabola that start at the origin, okay, again, hopefully you're noticing a theme here. Pay attention to where these constants show up. Okay, something that's underneath here is obviously different from being outside the radical. So that's going to make a difference when we start looking at some of these transformations. Okay, so these are our 6 parent functions, and now we're going to start messing with them with some of these transformations that we're going to look at here in the next topic.